Grieve. My name is Una and I'm from theharpteacher.com. If you've ever tried tuning your harp with the tuning app or with an electronic tuner, you've definitely experienced needle jump. That's my term for a phenomenon where the needle on your display will jump wildly, seemingly irrationally, from, for example, the sharp to the flat, or maybe even from one note to another. So this makes tuning even more difficult and time-consuming than it already is. In this video, I'd like to explore some reasons why it happens, and then we're going to be in a far better position to solve the problem. So let's go. So what exactly am I talking about? Well, here I am with my harp, and I've got the Clear Tune tuning app for Android right here. What I'm going to do now is I'm going to pluck a string and show you the reaction on the phone. So if my beautiful assistant could move in so you can see the phone nice and clearly. Okay, we all ready? 3, 2, 1. So I wanted to be able to show you exactly what's going on with that needle. So what I've done is I've taken the video of the string being plucked and I've slowed that video down to approximately 1/8 of its real speed. Now let's look at it and see what really happens when you pluck a harp string. So we start off with C sharp at -2. Then it moves to C sharp -5 around. And then we go to C sharp -10. Then it goes back to C sharp around -5. Then it goes back to C sharp -10. Which is it? -5 or -10? I don't know. And then it gets really exciting. It goes to A, if you don't mind. And it's a really sharp A. It's plus 35 cents. Then it goes to C sharp -22. That's incredibly flat. Then it goes back to C sharp -9-ish. Then it goes to C sharp -6. Then it jumps to the A again, but this time the A is in tune, plus 2 cents, that's all. So what is going on? Is it a C sharp or is it an A? And now we're at C sharp -9. Then it jumps to A plus 7. What is going on? Which is it? And then it's A bang in tune pretty much, A plus 1 cent. So far, that is 13 different readings. When I actually looked at the entire reading, it took 5 seconds, but there was 29 different pitches given, scattered between an A, a C sharp, and an F sharp, and varying degrees of sharp and flat. 29 different pitches in 5 seconds is physically impossible to read. Why is this happening, and how can we improve the situation? So my Christmas present to myself this year was an app called iStrobosoft, and it has a really cool add-on which is a spectrometer, which simply gives you a visual representation of sound in time. So what's happening here is that iStrobosoft is going to visually represent my talking. So if I talk really loudly, you can see that the sound goes up. If I talk softly, the sound goes down. So the loudness or amplitude is measured by how high the line is. The pitch, or whether the note is high or low, is measured across the top here on the horizontal axis. So if a line appears here, then it's a G sharp. If a line appears next door to it, it's a G. If a line appears here, it's an F sharp, etc. So let's see what happens when I use my whistle with this thing. So what I heard there was one pure note, but actually it wasn't. Check this out. My first peak on the spectrogram says this C sharp. No surprises there, I played a C sharp. But then there's another peak, and it's the C sharp an octave above that. What's going on? A second note? And then there's another peak, a G sharp. I mean, what? Well, it turns out that the air through a whistle or a string in a harp don't vibrate in one simple singular way. In fact, they vibrate in lots of different ways at once. And this is a science entirely on its own. So it's beyond the remit of this video, but I've put a link to an explanatory article in the show notes beneath this. And if you're interested, go and click on that after you've watched the video. So the first thing to observe is that the bass volume in my apartment is somewhere around here, just under -100 decibels. So I'm gonna just ignore everything that's happening around here. Okay, so how many peaks are there above -100? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There are 16 different notes in that one whistle sound, which I just played. So let's look at their loudness. This one here is actually approximately -30. The quietest one here is around -90. That's a really wide range. -90 to -30 equals a range of around 60 decibels. So what's really cool is that even though there are 16 different notes making up that one whistle sound that you heard, one is very definitely the most powerful, okay? So this is all illustrated in decibels, which are logarithmic. And if we look at this peak here, the C sharp is -30 decibels. It's so very obviously taller and higher than the rest. We know it's probably the most important. But if you look at the maths of it, the next one is actually -50. There's a 20 decibel difference between this and this. That means that this note, the C sharp, is 100 times louder than this second note, the high octave C sharp. So it's really, really clear from the scale that there is one note out of the 16 that is the loudest, that we will hear the most, and that is probably the most important to tune. Now, what I really like about this software is that this software has been invented or designed so that it realizes that. So it's got an X above that C sharp, that loud C sharp. And when I tune my C sharp, it will only pay attention to that C sharp. It will actually ignore the other 15 of the 16 notes that made up my whistle sound. So now, let's see what a harp sound looks like on a spectrometer. Wow, okay, first learning, this decays incredibly quickly. So I'm gonna do it again, and this time I'm gonna pause just a millisecond after I pluck. Here goes. So this is so fascinating. It's the exact same note, but what a different picture. The first thing to observe is that decay that I mentioned. So look at this. I have lots of high volume to here, and then a very sudden, sharp stop to all sound. It goes to virtual silence from there on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that one sound that we heard was actually made up of 10 different notes. This peak here is around a G sharp. This one here is around a G sharp 1 octave higher. This one here is an E. This one is a C sharp. That's the note name I actually plucked. This one here is a C sharp, also an octave above that. And this one here is a G sharp, etc., etc. So let's examine the range of the different volumes of these peaks. So the quietest one is -90. The loudest one here is -40. So it's got a range of 50 decibels. So what's the volume range of our loudest peak and the second loudest peak? Well, our loudest peak is around -40 decibels. Our second loudest peak, -50. So our range is approximately 10 decibels. Remember, decibels are logarithmic, so that means our loudest peak is 10 times louder than our second loudest peak. That might seem like a significant difference, but compared to the whistle, it's nothing. If you think back, you'll remember that the loudest peak in whistle is 100 times louder than the second loudest peak. In essence, what happens when an electronic tuner is listening to a harp is that it's hearing all of the frequencies, and because they're so close in volume, it just gets confused. It's like, oh, this is the loudest. No, this is the loudest. No, this is the loudest. And that's why that needle jumps all over the place. And now we're in a far better position to actually solve that problem. So hit subscribe to get any new videos from the harp teacher, and then hopefully you'll see our next video, which is where we look for solutions in how to solve this issue. Slán.